plus mu dn. Now, mu dn, we haven't talked about. We haven't gotten to there yet. But for a single component system, there's still what's called a chemical potential, which literally is just defined as the change in the internal energy or the change in the number of moles holding S and V constant. These partial derivatives you may not feel that comfortable with just yet, and so you can write it just in terms as a variable if you like at this point, but also realize that this you will get more comfortable because thermal is there's all over the place. But anyway, chemical potential we'll talk a little bit more about, and it will definitely, when we get to phase diagrams, that is one of the key variables right there is chemical potential. And we'll also talk about what each one of these means in a slightly different way. For now, this is a pretty it's a pretty consolidated form of the fundamental equation. It's for a simple system, meaning there's not any sort of magnetic field or something acting on the system. The only thing we're considering is that, well, what we now know sort of through the first and second laws. But we're also not even considering more than one component. So the only type of problems we can tackle at this point are like water and steam, because it's all water, a single component system. And of course, there are, a lot of interesting phenomena that happens with a single component system. For example, water going to ice or water going to a gas. That is an interesting phenomenon for a single component, but we'll largely be more interested in multiple components going through phase changes and things like that. That's sort of the cornerstone of a lot of material science, is understanding phase diagrams of those things. So we will need to be able to write this for not just a single component. This whole problem is recognizing that U is a function of not just S, V, and just N, but also of multiple components. So you could think of a two-component system, a real-life example, ethanol and water, one of my favorite mixtures. So you would, in that case, it would just be N1, N2, where it'd be in ethanol and in water. So the question is, can you do this same analysis that we did here, except for multiple components, sort of a generalized form? So with that, see if you can write it out. See if you can write this form here for expanding essentially this in the total derivative, but try to write it in this generalized form where you can have C number of components, where C is an arbitrary number of components. So for ethanol and water, C would be 2. Should give you some practice on doing those partial, expanding the derivative. It's a good thing to practice. It's certainly not the last time we're going to do it in thermo. Okay. I am going to attempt to do this live. So we're going to start with the partial of U, right? That's what I'm asking you to solve for. And we can write du I'm just going to pick the first variable and do the change in that, holding the other variables constants. So that would be v and in sub I ds. So just notation-wise, that's the first term. It's a little hard because you'd have to write in what you could write in one dot 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 to in C. I'm going to use this notation of in I, assuming that it's all those, it's all of them. Another way you can write this, it's in other books, is that this is maybe a little bit more foreign, or I don't know, it depends on what class you took and how they took it. That also can have a bar underneath it saying that it's a vector. In other words, it's a whole bunch of series of things. But I'll stick with the notation of I. Okay. Because I can copy and paste, I can do this next one really fast. And so that's what you should have gotten for the second term. Now the trick is the third term. How do we represent all the other components? And I said the hint is that we probably need to use a summation. And again, a little bit, it's going to be a little tricky about the notation. I'll show you that in a second. So this is the ultimate answer. Okay. It's the summation from I equaling 1 to C. So we're just going to sum all these terms. Let me do a little bit more clarification here. Just to, you don't have to do this, but so you still have to hold, so you're changing the internal energy with respect to one component in I. Let me make this really much bigger so people can see all the little stuff I have there, right? Okay, so this is I equaling 1 to C. Changing U, the change in a very specific component by holding the number of moles of all the other components constant. And we symbolize that by just saying J, where I is not equal to J. Okay. So if I were 1, that would be du is equal to d. Let's say it's a 3-component system, just to make it a little bit more complex. This would then be du dn1, s in 2, and then in 3. The next component would be du dn2, holding s and n1 and n3 constant. Okay, so you're not holding the one constant here, or else that derivative wouldn't mean much, right? And then you're just changing. This is just the same sort of form as these others. Does everybody see that and could do that themselves now?
Would you also hold v constant? Or
Oh, yes. Haha. Very good. See, this is what happens when you do things live. See, I would have got 9.5 out of 10 for that one, right? So we could also write, let me just move this around just a little bit. We can simplify this a bit. And I would prefer you make sure you always show your work when you're doing your homework. If you just jump this next step, you'll get maybe a 7 at best, but you're not really doing the work if you just jump to this next step. That can be, oops, that's not what I want to do. This next term, you can recognize du ds at constant v, holding all the moles constant, as t. So you can write that as ts. Let me just keep my equal sign in front here. And then I can recognize this other one, du dv, holding s and n constant as minus p. So the minus p is actually, it may not seem clear why we add a minus p rather than just p, because literally we could have made it any variable. The reason why it's minus p is because we want it to relate to the pressure. Again, we'll talk about like some of the more physical forms of this in just a bit and sort of justify why it should be minus p. And then at this point, we don't know much about this other variable, but I'm going to put it in there, and I want you to start to just put it in your brain, this what's called chemical potential. And it looks like, let's make it fit a little bit. It looks like that. It's just mu sub I. Mu sub I equals this whole term here. So you don't have to write this for this homework problem. You just need to be able to write this. But I want to make the connection that this, all that is T, all that is minus P, and it just comes out of when we do the analogy back to heat and work, and then ultimately chemical potential, you'll see. At this point, mu sub I is as foreign as this, and so it doesn't really matter what it is. And I will sort of, we will learn how to understand how to use chemical potential to calculate problems. And you might start to verge on understanding its physical meaning, but you probably won't ever completely, it'll become a mathematical tool rather than, it's a little difficult to say it's like a pressure. Pressure, you know what pressure is like. It's a force over area. Everybody's blown up a balloon. They know what pressure is, right? Tire pressure. We use pressure all the time. There's also ways of measuring pressure. Barometers, right? We don't have a chemical potentiometer, so that makes it really hard for us to fully accept or understand. Hopefully with this class, it'll give you a little bit more intuition about it, and you'll at least be able to use it as a mathematical tool to calculate things like phase changes and such. Okay, again, a little bit of foreshadowing, so if some of the words aren't completely connecting with you, that's okay. Hopefully by the end of this class, all these things I'm saying, you'll understand. Okay. And then this is the answer again, I guess. So let's go ahead and go back to presentation mode. All right. There's also another thing I wanted to share with you, and that's partly because you'll see for a one component system, a lot of times you don't